Good evening all.
Good evening.
Maybe we can wait for 2 more minutes, couple of minutes, or maybe we can get started. So before getting started, are there any specific queries that you want me to address in this week's sessions or the previous weeks? Yeah, if there are no questions, then maybe we can get started. So this week starts discussion on convolution neural networks. So the first question that is shown on the screen right now is not a CNN, but the concept is on something called receptive field, which has been discussed in the sessions, in the lectures as well. So in this particular 4 options, so if I consider, say, for this particular neuron, in each one of them, which one of them has the widest receptive field? By receptive field, I mean like this output should be able to see all the possible inputs that have been given. In order to decide the value of Y3, if that particular network is chosen in such a way that it allows all the values of the inputs to be seen, then it is said to have a wider receptive field. C has a wider receptive field. Okay, all of the answers are on C. So if you happen to see this, so for the first option, you have connections to H2 and H3, and from H2 you have, so from Y3 is able to see three inputs, X2, X3 and X4. For the next case, it was able to see all the inputs. If you happen to see B option, even in case of B, you have Y3 being able to see all the inputs. So if you happen to see, like in this particular example, both B and C have same receptive field. So which one of these two networks do you think will be more suitable for a given application? We cannot comment directly on the suitability, but if you happen to see the number of weights, C has more number of weights compared to B. In B you have 6 plus 4, 10 plus 14 and 15, 16, 17 I guess. So there are 17 interconnections here. Connections, and how many connections do you have here? 20 connections here. So you are able to get the same receptive field both with 17 weights as well as 20 weights. So computationally this is better than the third option. But will it be able to capture the outputs depends on that particular data set you are trying to use this model on, which we will not go into. But for now, I think the concept of receptive field is clear. So we'll go to the next question. So this week essentially discusses on convolution operation. So if you do a convolution operation, which of these following 3 transformations will be that particular operation invariant of? By invariant, I mean, say if you have some image I, and I'm applying some convolution transformation on it, say this is used for convolution, say I'm using this for convolution, times k, I will be getting some output yes. Now what I'm trying to say, if any of these operations is denoted by t, if I apply t times I and then apply convolution, say I got S1, alternatively I do convolution first and then apply the transformation operator on that. Even then, if I get, if it is S2, if S1 equals to S2, then I am calling it invariant. So why do I need to know whether these particular operations will be invariant or not? Is because when you are giving your training data, if you know that the particular operation is not invariant to these transformations, then you have to include those transformations in your training data itself. Otherwise, it won't be able to learn these transformations. For example, if you are solving a CFD problem, okay, let's take a general example. So if you want to identify, say you have an image with some irregular object in it, your objective is to identify this particular object inside the image. So if suppose the same image, if the object is rotated, say like you can take your face as an example. So if I rotate the image by say 10 degrees or so, or 20 degrees or so, so if the object now becomes tilted at some angle, so initially it is at like this, now it is tilted. Now if this particular operation is not invariant to rotation, then both of these examples should be present in the training data. Only then the network can learn these kind of relations. So in order to decide your training data, this invariance is something that you should be aware of. So which of these operations do you think convolution operation is invariant of? How do I know if it is invariant or not? So how do I write mathematically the convolution operation? All of them are invariant. Okay, so how can I decide whether it is invariant or not? So any basis on which you have given this answer, that all of them are convolution is invariant to all the three options? Say if I have a 2D image, I am denoting with I of I comma j, or basically I can write this as, say if S of ij is the result of my convolution. How do I do convolution? I have an image. So what I am doing is I am taking a kernel and I am passing it on the grid. So it is essentially summation of along x and y directions. Say if I is my input image, this is at a given index, so at that particular index plus whatever kernel you will be using, these indexes depend on those kernel. So summation over m and n times whatever kernel you are using times m comma n. This is what you are doing essentially. If you want to implement it in any, like if you want to implement it using Python, this is what you will be doing. You will take the kernel, you will loop over the elements of the kernel, and then you will loop over the elements of the image where you have an overlap between image and kernel, and then you take a summation of all of them, and then you take a summation of all of them. That's how you finally attain the value at a given index I comma j. So now the question is, if I want to apply a translation operator, so how would I do that? So if I prime is my new image after applying the transformation, so I prime of I comma j, how do I obtain that? Is I take the original image and then apply linear whatever transformation we are applying. If you apply a linear transformation, what is happening is the intensity in the image previously at I comma j is now being transferred to I plus tx and j plus ty. That is what we mean by translation. So now if I do convolution on I prime, say I get an image S prime, is essentially sigma, and so I am just denoting with one sigma with two indices here. This is equal to this, just as shorthand notation you can consider, but ideally you should have two sigmas. So it will be I prime, I plus n, j plus n, this is essentially equal to so say if I put a new index here, it's like, or you can consider this I plus tx plus m j plus ty plus n. This 2 is essentially one variable and this 2 is essentially another variable. So this can be written as, if you use the original formula, this equation 1 here. So if I substitute 1 here, so this is essentially equal to s of I plus tx. Instead of I am having I plus tx here and j plus ty. So from equation 1 I can write this, right? So your s prime of ij is obtained just by taking the original convolution and then translating it. So convolution is invariant to translation, which means you don't need to have translated images in your data. Now coming to the next case, for rotation, how do I denote I prime? I prime is the image obtained after rotation. So we have discussed this before. So image is essentially a matrix. So if I want to apply a rotation, so I can all these operations can be denoted with matrix multiplication. So if R is my rotation matrix, I can write R times, I am just using dot here, which means a matrix multiplication, I of I comma j. So with this particular notation, if I use S prime is my resultant image after convolution. So that is sigma mn R times I. For this I have to do I plus m, j plus n. So now in this particular case, what can I say about this? Can I bring this R out or something? This rotation matrix, this matrix multiplication is something I have to do, and then I have to apply this I plus n and j plus n. I can't bring this R out of this summation. So I cannot write this as, this is essentially not equal to 1. So if I were to translate this, so if I am writing S double prime of ij as rotation of transformation, so that is going to be R times S of ij. So this, say I am calling it equation number, so this is my 2, this is my 3, and this is my 4. 3 will be equal to 4 only in the scenario where you can bring this R out of the summation, which is something we cannot do. We multiply first and then we apply the kernel on top of it, which we cannot bring outside of the matrix, outside of the summation. So 3 and 4 will not be equal. So convolution operation is not invariant to rotation, which means when you are training a particular network with images, so you need to ensure that your training data has all the rotated versions also in it. So this is something called data augmentation. Data augmentation is, say you have a few images of faces. What you do when you train your network is take those images, apply rotation operator on to all those images and create a new training data from it. So if you have 100 images, with those 100 images, for every image you create say 20, 40, 60, like rotate it by different angles and then get new images, and then make this 100 data set into a little higher data. So you can get 400 samples now after applying say 4 transformations. So this is for the translation part. So what about scaling? Now if you follow the same process for scaling, what do you think you will get? Maybe you can try it, I'll give you a couple of minutes. So apply the same logic. Scaling is essentially, I'll write the first transformation for scaling, so you can proceed. Yeah, you have something to say. In scaling, what we are doing is I prime of ij is some scaling factor. Say gamma is my scaling factor. Gamma is the scaling operator. So scaling operator will be, say if in 3D it will be something like some scaling x, y, z, and then you have all other components to be 0. This could be one scaling matrix depending on whatever your dimension you are. So this could be gamma. What we are doing is we are doing a matrix multiplication of gamma with respect to I of I comma j. So this is what I meant by scaling operation. Now if you do this, calculate S prime of ij using this. S double prime of ij will be gamma times S of ij. So my question is S prime equal to S double prime? You can quickly do this and let me know, are you getting both of them to be equal or not? You can follow the same process as I have done for the previous case, for rotation or translation. No? Any other answer? So instead of R, you will be just replacing with gamma. So we'll have sigma mn gamma times if consider a scenario where all these three are equal, kx, ky, kz, and it is just some constant. In that particular scenario, gamma can be written as some constant, say gamma naught times identity matrix, right? If all the scaling factors are constant. For that particular scenario, if all of them are equal to one particular constant, only in that scenario I can write this as gamma naught times s of ij. I can bring gamma out of this summation only in that scenario when you have this to be equal to a constant throughout the image. It's like basically I have taken an image, I have scaled every intensity in every pixel. So all the intensities are scaled by the same factor. So it's what happens is if you apply convolution operation, you are going to get a different answer, but however the different answer will still be linearly proportional to the previous one that you get without scaling. So maybe S prime and S double prime may differ in magnitude, but the patterns that you get will be going to be the same. So if it is equal to gamma naught here, then I can write this directly as gamma naught times Sij. So both of them will be equal only in that particular scenario where you have uniform scaling across the image, which is something you might not always come up with. So locally you can scale specific portions of the image and then do your data augmentation from that. That way you can increase your training data and then your model from that. So now is it clear? So now what the conclusion is basically convolution is invariant to translation, but rotation and scaling it is not invariant to. It will change depending on these two. So you can do data augmentation by actually rotating and scaling your original images and then creating more data from it. Now at this point maybe I would like to ask another question. So when we were discussing on optimization, we told that if you have say n variables and m equations, we discussed that we are using optimization because you have okay, let me ask, so which of these is the scenario where you use optimization? So out of these three cases, which one do you think you will use optimization for? Or I can use for any one of them, any of these two combinations A, B, C, all I can use optimization. Consider this to be a multiple choice. I mean, you can choose more than one option as correct, so maybe I'll put all of the above. So is the question clear? So when do we use optimization? If you have say n variables and m equations, in which of these following scenarios you will be using optimization? So why, okay, let me put this in context. So previously when we were discussing, so you heard that we were having some parameters. So what we are trying to do in ML is basically you have some parameters or weights and then you have some data. So this data is essentially equivalent to your number of equations and weights are essentially equivalent to your variables. And then we understood different cases of underfitting, overfitting and different cases. So and we in one of those scenarios we were saying if your model is not performing good, there are some scenarios where you need to increase your data. Essentially you need to increase your equations or you can increase your model complexity, which is essentially increasing the number of variables. In both these scenarios you are using some optimization routine. So in which of these scenarios, okay sir, he is mentioning that we will be using n greater than m. So essentially your number of variables should be greater than your equations. So if you have more variables, and less number of equations, so you would be needing optimization. Okay, let me put the question slightly differently in this particular scenario. So if you have more variables and less equations, so why wouldn't you be able to get more equations? So you could try to get more equations, like make it more constant and then solve it, right? Okay, you would say maybe I don't have enough data. So let's relate this with whatever we have right now. So your weights are essentially the unknowns that you are trying to solve for in any ML problem. So the weights are essentially your variables. Data is essentially the type of constraints you are imposing on your model. So these are the constraints or equations that the model has to satisfy. So your data is symbolically, like you can say analogically, to be equivalent to your number of equations. It's not necessarily equal to number of equations, but it can be kind of related to equations. So what we wanted to do is, when you are doing an optimization, we have a certain number of variables and we want to satisfy all these equations. So what you are doing is you are essentially bringing in more variables so that it will identify some optimal problem where your whatever error or objective function is minimized. So in the scenario where your model is not performing better, then what you do is try to increase your equations. So this will ideally reach this scenario where you will have a unique solution. Only when n equal to m is when you have unique solution. So initially, if the model is not performing, you try to increase your data set. This is something that you will see in CNNs. But the problem with the convolution, as we have seen before, is it is not invariant to these two other operations. So what you try to do is increasing your data set so that you will eventually reach this scenario, so that you will be able to find some solution, some better solution. But you should still be in this region for your optimization to work. So ideally your n should be not exactly equal, but closely to m. You will have a better solution. Is this clear, or did I cause more, or did I create more confusion or something? No? Yeah. If there are no questions, then maybe we will go to the next one. Okay, now convolution operation is done. So let's talk about pooling operation. So what do you think pooling operation is invariant of? I mean, not think. So what happens in pooling operation? I'm just saying it's not max pooling, it's average pooling. Instead of max pooling, I'm using average pooling. So if my kernel is 2 by 2, whatever is overlapping in that 2 by 2, I'll take sum of all of them and then take an average. Okay. One answer is scaling, so it is invariant of scaling. So others, any other different opinion? So why do you think it is invariant to scaling? So what are we doing in pooling? Is just we are in this average pooling, is you take an input image. So this is the overlapping region, say 2 by 2 kernel. So you have different intensities. So this will essentially come to a single pixel with, say, output equal to the average of all of this. This is what I meant by average pooling. So if you do this, so why are we doing pooling operation anyway in our CNNs? There could be several reasons, but let's say if it is invariant to scaling, will it be of any use to me that I need some operation that is invariant to scaling? I know previously that convolution is not invariant to scaling. So I am introducing a new operator which is invariant to scaling, that is pooling operation. But will it be of any use to the network as a whole by introducing this pooling operation? So why is it not invariant to translation and rotation? To reduce the dimension, yeah, that is fine. So I was asking, like, from what we discussed in the context of what we are discussing right now. So we told convolution operation is not invariant to scaling. Now you mentioned that pooling operation is invariant to scaling. So now I have a CNN which doesn't obey scaling. I'm just putting not equal to. So what we are doing is we are we are doing a convolution for, and then we do a pooling after this. So now which is again, this is invariant to scaling. So you are doing operations in a sequence, first convolution followed by pooling. So initially something you are doing which is invariant to scaling. It's like basically if you scale the input, then the output of your convolution is going to change there itself. After that you are applying pooling operation. So what advantage do you get by this invariance to scaling? By keeping this pooling layer after convolution layer. Is my question clear? So basically you have an input and then you do some convolution. So let's say x is your input. You do a convolution, you get x1, and then you do a pooling, you get x2. So if this particular image is now scaled by k times a constant factor, like, or some scaling factor, let's say s is some scaling factor, you scale this image. Now if you do convolution, you are going to get some different. It's not going to be s times x1. This won't happen. This will happen only when s is a constant. So it would be something else now. So it will be x1 prime. Now on x1 prime you are applying pooling. So you get x2 prime. So this pooling operation you are trying to make it scale invariant. Why is that so? Why do I have to do something like that? Or is it going to be scaling invariant or not? So do you stand by your previous question, like previous answer, that it is invariant to scaling? It will reduce the dimension for sure, but are there any other advantages with pooling? Okay, so what we are trying to do is we are taking average of 4 different cells and then coming up with a mean value over there. So this is some kind of summary of whatever previous layer has. So this is not going to change. Say suppose you have some outliers in your original data, some noise in your data, which is something that we want to get rid of. So basically what this does is it is making your model more redundant or more robust to these small changes, or what I call local defects is something I can call, or basically if you have some minor changes. So if this is your original image, you have several people or maybe several faces. So if you have something like this, now if this image is slightly changed, so if I shift this slightly, so what my neural network does is it would treat both these as different images. Ideally for us, say if you want to do face detection, so if the face moves in the frame, it should actually be able to identify that. Instead of saying that these images are completely different, it should be able to identify this face. So if this is my 1, 2 and 3, if 1 is slightly shifted, so if I slightly shift 1, even then it should be able to identify that it is still 1. So this small local, by shifting these local ones, you are not going to change, you can change your individual intensities, but the mean value is not going to be affected by that change. So if you do a pooling layer and use that as an input layer to further downstream, after doing pooling you send this as the input to further downstream. So whatever layers that are present in the downstream will actually identify, will actually have these mean values as the input. So changes like this will be equivalent to it. So it will be invariant to translation, rotation, scaling. It will be invariant to all these operations because you are just taking a mean value of all the cells that are present, provided that these are small enough. If this one is moved to much longer distance, then it wouldn't work, but as long as these changes are little to the size of the kernel that you are using, then it should be able to tell that both, say if this is my image 1 and image 2, after doing pooling operation it would treat both I1 and I2 to be similar. Is that clear? So it will be invariant to these small transformations. So now in engineering applications, say if you are doing some CFD simulation, I don't know how many of you are trying to do. I think you are from different backgrounds. So if you have a specific application where your location of objects, say if you have a scenario where you want to predict the flow field in a certain scenario like this. So let's take a simple example. So you are in a room and then you have some fan here and some air is blowing over that. So your particular location in the room should actually dictate how you feel. So if your position is changed inside the room to a different one, it should have a different solution than the present one. So things like this, in scenarios like this, if you use pooling layer, it would treat both 1 and 2 as equivalent, and it will give you the same answer. So in those scenarios, you shouldn't be using this pooling layer directly. Is this clear, or are there any queries? I guess it is clear. If there are no queries, then we'll go to the next one. So there are a lot of assignment questions this week on how do you determine the sizes of output layers and so I just put a small question here. So if K is my kernel size, P is the padding I am using, W is, say it is a 1D convolution. Yeah, I think you just left. So what we were discussing previously is if you use this small transformation, so if 1 is here, it got slightly displaced. In scenarios like this, if you use pooling will take average of all the intensities that are present in that given region, so that mean value is not going to change drastically for these small transformations. So if you use pooling layer, it would treat both I1 and I2 to be same. So it will be invariant to these any of these local transformations. That is the main idea for pooling. And I was giving an example where you have a room with a room with a fan, and then human can be at 2 different locations. So if you want to identify the flow field inside the room, the case for 1 and 2 should be different. If you use a pooling layer in that scenario, it would treat both 1 and 2 to be same and will give you the same answer, which is something that we don't want. So you shouldn't be using pooling in layers in scenarios like this. But in most of the image processing tasks, we will use pooling primarily to reduce the dimension, and then most of the cases with, say, object detection or face detection or things like that, yeah, is it audible?
Yes.
Yeah. So where was the connection lost? Okay.
You repeat one more time.
Yeah.
Otherwise.
Yeah, fine. So we were discussing on the pooling. So why do we want to do pooling is because if you have, say, this image 1, I1 and I2, the only difference between I1 and I2 is this 1 is shifted by little. So in scenarios like this, when you take an average, the average value is not going to change drastically, so that whatever filters that you use on the further downstream will not identify I1 and I2 as 2 separate quantities. They will identify both of them to be same if you use an average value, and this average should be like within some particular domain, like some particular region. So this is why we use pooling for. Now I gave an example where pooling is not required. Say if you have a scenario of a room with a fan and the air is blowing over that, so human can be in either position 1 or position 2. So depending on his position, the flow field in the room will be changing. So if he is in 1, it would have say one kind of flow field, and 2 you can have different kind of flow field. But pooling will, if you apply a pooling layer before the final output layer, it would actually treat 1 and 2 to be same. Because it is invariant to this translation, it would treat both of them to be similar. that is something that we don't want. So in those scenarios, you shouldn't be using the pooling layer. So is that clear? Are there any questions in this? So the answer for the question is, if these whatever transformations you are applying are, if they are small enough, then a pooling operation is invariant to all of this. Yes, clear. So let's go to the next question. The next question is on how do you find the size of output after you apply a convolution layer. So we have seen there are k is my kernel size. This is for a 1D convolution or convolution along one dimension. You can vary the dimension. So if it is a 2D matrix, you apply the same thing along two different directions, but the idea is going to be similar. So if you have k as your kernel size, p is the padding, which I will do on either side. So padding is done only on the boundaries. W is my window size, or basically the input size. So what, when we apply the kernel, so 1 is my starting index, 1 to k is what the kernel size, and then I move the kernel along the direction, along one direction. So when I'm moving, I need to come up with this stride. S is the stride. So I can either take stride to be 1, 2, 3 or any higher number. So it can be from 1 to k, and then you do it from 1 plus s to k plus s and so on. You do till the last step where this will be equal to your final matrix. So when this is equal to the final one will be W plus 2p equals k plus n minus 1 times s. That is what I have finally. So if I just equate, n is basically what will be the output size. So n will be equal to W plus 2p minus k by s plus 1, where p is your padding, this is my input size, kernel size, and this is the stride. So this is clear. So now if we put the question reverse, so if I want to apply a transposed convolution, which is reverse of what we do in convolution, it's not exactly reverse, but the idea is, if you have say basically if you want to reduce your size, you use convolution. If you want to increase the size of increase the resolution of your image, you will be using transpose convolution. So what would be the size after you do the transpose? It's just going to be reverse of whatever we are doing here. So the idea is, in transpose convolution, this is going to be your output. Say, let me say this as x, and whatever I get here, n as y. So this is my output. So in convolution, this is what we are doing. So what I want to do in transpose convolution is just the reverse of it. So in transpose convolution, n is my input and w is something that I want to find out. So how do you find w? So you can just equate from this, n minus 1 times s plus k minus 2p is going to be w. So if you want to do a transpose convolution with, if p is my padding, k is my kernel size, s is my stride, and then I want to do a transpose convolution, n is my input size. After doing the convolution, your output is going to be of size w. W will be equal to this particular equation. So this should be straightforward. So I have not given any specific numerical values here, but you should be able to calculate from the expression directly. So I'm not going much into this. So but there are some questions in the discussion form asking how do you do this transpose convolution and stuff. I don't want to give numbers because it is a graded assignment. So I've just taken a small example to illustrate how this works. So if you have a 3 by 3 matrix and you are applying a 2 by 2 convolution with stride 1 and 0 padding. Okay, you have already seen the answer, but what will be the output size here? From whatever we have seen previously, so output size is going to be w plus 2p minus k by s plus 1. W here is 3, padding is 0, kernel size is 2, stride is 1 plus 1, times you have the same thing coming again. So this is going to be 2 by 2. So what we want to do, the idea behind transpose convolution is, if you were to represent this with a matrix operation. So what we have, so this is my matrix. So maybe I'll use input as x. this is my input and my kernel is denoted with W, the weights that I want to find. So now what we will do is take this kernel, apply it first on these 4 elements, and then you move it, then you move it, and finally you move it. So there will be four different ways, and you will get all these values. So what now the idea here is we can represent this operation using, like we discussed previously also, like any of these operations can be denoted with matrix multiplication. So now if I want to denote even convolution operation with a matrix multiplication such that, so if x is my input, I am doing some operation c times x equals to y, y is my output. But in order to do this, x cannot be in the matrix form that we have in this way. Instead, I will convert x into a 9 by 1 matrix. So initially x is a 3 by 3 matrix. I am trying to convert it into a 9 by 1 matrix. Essentially it is going to be like you just write them in one sequence, something like this, x21 and so on. So like this you will have a 9 by 1 matrix. Now I want to map this matrix with some convolution operation. So this is my operator. The output is going to be 2 by 2, so it is finally going to be a 4 by 1 matrix. So my input is 9 by 1, output is 4 by 1, so the transformation operator should be 4 by 9. So this you get from the matrix multiplication rules itself. So now how do you fill in the elements here? So let's do the operation. So if we put the kernel, so W1 will be multiplied by X11, so I have this here. Next followed by W12 with X12, so W12 comes in the next position. The third one is X13, but X13 will not be multiplied with the kernel here. X21 will be multiplied by W21, so I have the next position like this, and X22 will be multiplied by W22, so I will have W22 here. And all the remaining 4 will be nothing, so those are the zeros here. So this is how you get the first row. So the first row essentially implies when you place this kernel on the first position. So this position is essentially the first row. Similarly, the next step what you will be doing is you apply the kernel in the second region. So this second region should correspond to your second one. So in the second region, the first element x11 will not be multiplied by anything, so I have a 0 here. The next you have the weights follow the same pattern, w11, w12, 0, w21, w22, which is exactly same as this. And then all other remaining elements are going to be 0. This is for the second batch. Now similarly you do for the third one and fourth one. So for the third one you have first 3 to be 0, and then you follow the same pattern. So this is the same pattern that is getting repeated. Similarly for the last one you have the same pattern repeated. Remaining everything it will be 0. So is it clear how I got the matrix C here? Yeah, so I think there are no queries in this. So this is straightforward. So now the problem, or there are two things that I want you to understand here. One, if you see this matrix operation and compare with the previous one, so you can also treat this X as your input, where you have the first network that was produced was using, before convolution networks for image processing, was using a linear one. So basically you take an input image essentially as a matrix, and then you convert it into a single layer, so of 9 by 1 matrix. On this, this is essentially some operator, so you can treat this with a simple neural network or an MLP. So you can, this can be an ANN or simple neural network like your MLP. I'll write ANN for the simple neural network, where you have fully connected network, FCN. So maybe that is what is used in the classes, so I'll use the same one. So you can use a fully connected network. So if you want to relate a 9 by 1 with a 4 by 1, a fully connected network is going to be this. So the difference is now you have most of these weights to be zeros. So if you model this with a fully connected network, you are going to have lot of these weights to be zeros, which is something we don't have previously. This is essentially the professor was discussing something called the sparsity of the transformation. So the transformation matrix is going to have lot of zeros. So this way we are able to reduce lot of the computational expense. So since your matrix operation is where you have lot of, it's like matrix multiplication is order of n cube. So that is where you get most of your time, like computationally intensive one. So by actually having most of these values to be 0, you can actually reduce lot of time. Second thing is, previously when we were having these connections, we have all the weights to be distinct from each other, but now if you see, there are a lot of weights that have been shared across the layer. So W12 is shared in different places. It's the same value. All of these will have the same value. W22 is same. W is same. So this is something that is called parameter sharing. So these are the two features that are mentioned, like CNN will have, which is sometimes advantageous compared to the fully connected networks. So now coming to transpose convolution. So if we denote it in this way, this entire matrix I am calling as C. C is my convolution operator. C times X is going to be Y. So we know previously, like if X is of 5 by 5 or y, X is of 3 by 3, or Y is going to be 2 by 2. So your resolution will be decreased after each convolution operation. So now what we want, which is often required, is the inverse of it. So you would be given a low resolution image, and if you want to convert it into a high resolution image. We will see the examples of this in the next week, or not in the next week, maybe when autoencoders will be discussed, next or next to next week, where autoencoders will be discussed, is when you will understand why this is important. But even now there are some examples provided in the lecture videos if you go through. But the idea here is, if you are given a low resolution image and you want to convert it into high resolution image, what you would be ideally required to do is X should be equal to C inverse times Y. You can do this, but as we discussed previously, now this C is not going to be a square matrix, so doing this inverse right away is not possible. There are you can use a pseudo inverse and then find the C inverse and then do this, but in order to do that you need to have the original matrix C, and if you want to have the original matrix C, you know that if you see this matrix there are a lot of zeros, so unnecessarily you are wasting the storage. So you have some query? Someone? Yeah.
In this y you are written diagonally for both cross terms.
So Y is essentially a 2 by 2 matrix, right?
Yeah.
So I am writing it in single way. So you have Y as something like this: Y11, 12, 21, and 22. I can kind of, like, this is equivalent to writing in this way, right? I can convert into a 4 by 1 matrix. So I want to compare how a fully connected network versus a convolution network works. So if I convert Y to be something like this, then I can see the relation between fully connected and CNN, right? Your input is 1D, your output is 1D, so whatever connection is there, you can represent with this matrix here. Is this what you are asking?
Yeah.
Yeah.
There is no issue of striding.
In this case, I have considered stride equal to 1.
If stride is equal to 2,
Then you would have more zeros here. If stride equal to 1, you just had, so basically here the image is, so if you see this, here we have doing this block. If stride equals to 2, then you will directly go to the next block. So you will have, instead of W21 here, you will be having a 0. Maybe let's take another example. Say you have a 4 by 4 matrix, and then you are applying a 2 by 2 kernel. So your output is going to be 3 by 3. So now when you apply for the first 4, it's like if you want to write it in the matrix notation, sorry, this is 4 by 4. So if you expand it, it is going to be 16 by 1, and your output is going to be 9 by 1. So you are going to have a 9 by 16 transformation. So now if you apply your kernel, the first one is going to come here. It's like it's a 2 by 2 kernel, say kernel is 2 by 2. So the second one is going to come here, first, second, and then you are going to have 2, 1. So this and this you don't have anything, and then 2, 1 comes here, 2, 2 comes here, and then remaining everything is going to be 0. Now for the next stride, now you have, instead of this is the previous one, now instead of S equal to 1, you are going to have S equal to 2. So which means you will be starting from the third one. So first, second are going to be 0. Here you are going to have W11, W12, 0, 0, 2, 1, 2, 2, and so on. So if you see here, there was only 1 0 because you have just stride equal to 1. But now because of stride equal to 2, you have more zeros. That's it. All that is going to change is your zeros are going to change here. Number of zeros is going to be more. It's clear, right? Okay. Now coming back to where we were. So yeah, one thing I can do is calculate this inverse and then get like you use y, use C inverse and then directly get the value of x. But in order to calculate this C inverse, I need to store this entire matrix, which has a lot of zeros, and it is unnecessarily we are wasting a lot of memory on that. And doing this inverse is itself expensive. So instead of doing that, what we are trying to do in transpose convolution is we will use C transpose directly. So if C is of size 4 by 9, C transpose is going to be of dimension 9 by 4. So this is going to be 9 by 4, y is 4 by 1. So I can directly get x prime, which is 9 by 1. So C inverse is also going to have the same shape as 9 by 4. So what we were doing, instead of actually calculating C inverse, we are just doing C transpose, which is going to have the same dimension as C inverse. So when you apply the C transpose on y, you are going to get x prime of the resolution that you require. So the question now is, if I do this transpose and times y is going to give x prime. So is x prime going to be equal to x? No. So obviously x prime is not going to be equal to x, because C inverse is not equal to C transpose in general. So if both of them are equal, only that would be a very special case, but in most of the scenarios C transpose won't be equal to C inverse. So this and this are not equal. So when we do transpose convolution, the operation is like some information is definitely lost in that. So essentially you are trying to upscale an image, so you don't have some additional information. So you are doing some kind of an average. Like ideally what we would do is add some zeros and do some reduce the value intensities or do some other operations on it. So you are not actually trying to get the exact information that you have before. So
There is a question. In the assignment, like, the question number 8, we are getting a real number.
yeah, you'll get real number. So what was your question?
You are asking to make the output size 14 by 14 and the input is 1 by 7
Okay.
and the kernel size 3 by 3.
Okay.
So what are the side and padding values?
Yeah, we'll come to that. We'll come to that. So we'll come to that question. Like I cannot exactly discuss assignment questions since they are graded. So we will take another example with slightly different values and we'll do that. So is this part clear? How do you do convolution? How do you do transpose convolution now?
You got it.
Yes. So we will do it slightly different one, 5 by 5 to 10 by 10. Yeah, but before going there, let me ask one more question now. Yeah, now this is my C transpose. So I think in your assignment you are given y value and then asked to find x prime. So I think you should be able to do that from this right away. So you have to just do transpose of this and then multiply, you'd be able to get that. That's not a big deal. Okay, now coming to this question. So yeah, it is slightly different. So you have a 5 by 5 matrix, 5 by 5 input, and you want to upscale it to 10 by 10, and you want to do it using a transpose convolution. So how do you go ahead with this? So if we recollect the original equation we had before, so this was the equation we were showing before. These two, let me take both of this. So this is for the normal convolution. This is for the transpose convolution. So now here this is my input n. Okay, let's say n is given as 5, w is given as 10. So if I substitute this, 4s plus k minus 2p equals w is 10. Yeah, now I have one equation and then I have three unknowns. So we're not going to have, three variables and one equation. So I'm not going to have a unique solution. So I can have different answers. So let's take one example, each separate case, and then we solve it. So first we will say I have s equal to 0, and I have another relation that k, p and s are going to be integers. All of them should be integers. That is another constraint that I have.
One thing in the convolution, transpose convolution equation,
Yes.
n stands for the input side of the image,
Yes.
w is output.
So n you apply convolution, and then you are going to get W. This is what I am saying. So this is what, this is N. Or maybe then I should reverse these two values maybe. Okay. Sorry, these values are reverse. So W, if W is your input, if you apply convolution, you are going to get N. If N is your input, if you apply transpose convolution, you are going to get W. Yeah. Now this is clear. So this is what this is what the relation gives you. So okay. Now we have three unknowns and one equation. So you have many solutions. So one possible. So we should try different cases. So if I tell you that, sorry, padding is 0 and stride is 1, or let's not fix one thing. So because I already have another constraint, so let's take padding to be or stride equal to 1. So let's start with stride equal to 1. If stride equal to 1, so what would be my output? K minus 2p should be equal to 10, or k equal to 2p plus 10. So if I use p equal to 0, I get k equal to 10. It's like I have different solutions. P equal to 1, I have k equal to 12. But all of this will use bigger kernels, which is something that you might not always want. So you can try for a different scenario. S equal to 2. If S equal to 2, what is the case? K equal to 2p plus 2.
S equal to 1, it should be k minus 2p should be equal to
6, right? Yes. Thank you. So this is 6. So if p equal to 0, this is going to be 6. P equals to 1, this is going to be 8. Yes. So if S equals to 2, it's going to be 2. So again, p equal to 0, you have k equal to 2. Different scenarios. So you do not have one solution. You can have different solutions, but it depends on what the kernel size. Like here you have bigger kernels, which means you have to do more computations. Here you have smaller kernels. If the feature size is bigger than the kernel size, then you should choose. Depends. It again, we cannot comment on which one of them is best or not. But I wanted to point out one more thing here. So here we have assumed that you are trying to do 5 by 5 to 10 by 10 in a single step, which is always not the case. Ideally, what unit is not discussed, right? I haven't seen unit if it is discussed or not. So we don't usually do upscaling in a single step. So we can do it in something called cascaded transpose convolution. Essentially, we do it in step by step. So instead of converting 5 by 5 directly to 10 by 10, we can have an intermediate step in between, and then from there you can go to 10 by 10. So the intermediate can be anything. So it can be 8 by 8, 7 by 7, 9 by 10, 9 by 9, whatever. It depends on whatever kernel sizes you are going to choose. Say suppose I want to convert it into an 8 by 8. It's like something in between 5 and 10. So now using this equation, can you tell me what some possible combinations of S, P and K that will achieve this particular transformation? 5 by 5 to 8 by 8 followed by 10 by 10. Can you give me these values of S, P, K for the step 1 and step 2? Any possible combination. You can have multiple solutions, that is clear, because you have 3 variables, 1 equation. So you will have multiple solutions. Give me one possible solution that will give me this transformation. I'll wait for a couple of minutes so that you can try this out yourself. Four by 4 followed by 3 by 3 converges transpose convolution. So yeah, one thing is clear, both 1 and 2 are going to be transpose convolutions. So first one, you want to apply kernel of 4 by 4. So what are the stride and padding you are using? It's like you have to specify all of them, otherwise it won't be unique. Okay, stride equal to and padding equal to 0. Let's check if this is working. So if you are using k equal to 4, s equal to 1 and p equal to 0, what should be my output size? You use this equation. W is going to be n is 5 minus 1 times you are using stride 1 plus 4 minus 2 times 0 is going to give you 8. So first step is clear. So what you apply for the second one is a 3 by 3 convol. So for this is for the first step, and for the second step you are using k equal to 3. Okay, you are using the same stride and padding. So W is going to give you, now you have size as 8 times your striding is still 1 plus kernel is 3 minus 0 padding you are using. So 7 plus 3 you are going to get 10. So this is one possible answer. There could be several other options, several other answers you have. This is one possible way to achieve this. Now let me ask you slightly differently. You could also achieve the same transformation. Say if I want you to use, do not use transpose convolution, use convolution and achieve the same thing. So will you be able to do that? I mean, you can add zeros anywhere inside, like you can add padding and then achieve it directly. So what I was trying to ask you is the same transformation, 5 by 5. So let's say instead of 8 by 8, we will first do with 10 by 10. Use only convolutions and padding, nothing else. Don't use transpose convolution. So will you be able to achieve this final one? So you can go through, use these relations to do that. So I'm just saying use normal convolution. So you should be using only this equation. W is 5 by 5 and is 10 by 10. So you can use any padding you want, any stride you want, so any kernel you want. So can you give me one possible combination that will give you this particular transformation? So I'll just write it down here, so everything will be in one place. This is simple arithmetic, but I just want you to do so that I have one more point to bring up here. So what I am saying is n equal to 10 is given, W is 5 is given. I want you to give me a combination of KPS that will satisfy the above relation. Any one combination. Is it possible, not possible? You need to get integers. All of them have to be integers. Is there any solution that will give you okay? 2 by 2 convolutions. Okay, let's see what he has told. K equal to 2, padding as 4, stride as 1. So if we use this, does this satisfy the original one? So let's say n equal to W is 5 plus 2 times 4 is 8 minus 2 by stride 1 plus 1. What is the size you are getting here? Sorry, 12 na?
14.
13 minus 2 plus 1, right? 11 plus 1, 12. Okay, 4 by 4 convolution, sorry. So if I use a 4 by 4 convolution, so this is going to be 4, 8. So even then it's not satisfying, right? 13 minus 4 is 9 plus 1, 10, right? I want n to be equal to 5. Sorry, okay, W input is 5, okay, n equal to 10. Okay, so we got n equal to 10 with this particular combination. 4 by 4 kernel with padding 4 and stride 1. So now you see that you have done 5 by 5 to 10 by 10 just using convolution and padding instead of transpose convolution.
Is kernel size, odd size, even size preferable or odd is preferable?
You would prefer odd, but you can do with even. There is nothing wrong in doing in even also, right? You can do it. But usually people don't do it because that you get problems with the edges and centering. So if you have an odd kernel, you can directly compute at the center and you can put that value there directly there. Something intuitive to understand, but there is nothing wrong to use or even kernel or something like that. So but now the question is this one. Yeah, that is what I was going to ask. Which one of them is better? Yeah, now you have convolution plus padding versus transposed convolution. So which one of these two do you think is better? We will come to reason as why one is better than other. Though definitely one is better than the other. Not from the computational perspective, but from representation power. Okay. So what is happening in convolution plus padding? You are essentially adding more zeros which were not originally present to the boundary. So whichever elements that are there at the boundary. So what you have done is you have added a padding of 4. So which means, so if you have, so this is my original image. Now you have added a padding of 4. So it becomes like this. So original 5 by 5 image, what have you done is after adding 4 by 4 padding, what would be the size of output image if you add a 4 by 4 padding? It's like this padding will only done at the boundaries. So what would be the output size? So 13 by 13. So basically 5 plus you are adding on 2 times, 4 to 18. So 13 by 13. And then on this 13 by 13 you are applying a convolution which is 4 by 4. That is how you got finally this one. So now the question is, now you have added lot of zeros here which are actually not present, and these boundary elements whatever that are present here, when you are applying a 4 by 4 kernel, they are going to be underrepresented because you have lot of zeros and lot of them will be just going out. So whichever elements that are there in the boundary are going to get less representation, unlike your transpose convolution. In transpose convolution they are going to be like, you didn't add any padding there before like this. So there you are going to have same amount of representation for even the boundary that were there just like normal convolution. So this is something that is a problematic with padding always. So when you do excessive padding, you are going to underrepresent your boundaries. It's not just in this, it happens everywhere. So you have to be little cautious when you do this padding. Okay. So which one of these two is better? Is transpose convolution, is which we will be using. Even better one is if you can actually use the C inverse, like that is where you have exact. If you were to do C inverse exactly, then you should actually get back X directly, which is the ideal one, which is something computationally too expensive. So we are okay with C transpose and we are using that. And even though you are able to just get this upscaling here using convolution plus padding, you should not do it because it is going to underrepresent your boundaries, which is not always required. At least in CFT or some scenarios is something that these are the scenarios which are more important to you in order to determine your field inside. So you should not be doing things like this. You should not add zero padding. You should actually take care of them. There is something else, maybe I'm not sure since how many of you are familiar with CFT. So there is something called periodic boundary conditions. So instead of adding zero boundary conditions, when you add this thing, you can actually add different values there instead of zeros. Or maybe we'll not go into that. Maybe we'll discuss spins sometime next week or next to next week. That's when we'll bring into those other concepts. So now the last question. Yeah, it's already half the time. So do you have any other questions before discussing the last one? This is something that is not covered in the assignment, but I just want to bring it so that you'll have a complete picture. So you have any other questions before going to the last one? I think I covered all aspects related to assignments. If there is anything else, so you turn convolution to a matrix and transport it.
Regarding this assignment 6, the question number 1.
Okay.
We have been given 14 channels, and the filter, the colors, the filter size is 2 by 2, and the number of parameters that is needed.
Yes. So I think there was a correction in the question that has been given in the discussion form, if you have gone through it. So it is not mentioned that there are 10 filters. That is something that is missed in the question. I think a typo or something. So that's been discussed in the discussion forum. I think you have gone through that.
The first person I raised that question, but it was informed that there is nothing, no data is there.
No. Okay, but there was a correction in it. I think it's been announced in the discussion form. I don't know if you have gone through it, but basically the missing information is essentially don't have the number of filters in that specified. So you can assume the number of filters to be 10 and then see if the options match with it. So do you have any, how do you identify the number of parameters is straightforward. Your parameters are essentially your weights in the kernel. These are your parameters. So from there you should be able to calculate. The only missing information is you don't know how many filters are there. So you can assume 10. That should be sufficient for you. Yeah. Now coming to this, so how did I do this transformation? So is the matrix clear? Or you want me to explain how I got this matrix in the first place? Okay, you want me to visualize, okay. So matrix is clear. So what I am trying to do now here is I have a original image. I am trying to spread that image. Instead of writing it in the it's like you have a 2D image. What I am doing is like you have a paper. I am just tearing the paper into pieces along different width directions. So basically what I am doing is, this is my image. I am just tearing each of these pieces and then adding them across the length. So this is what I am doing. I am just tearing them and then adding one by one. So this is something that was done previously, the original handwritten data set. So instead of before convolution networks were there, this is what they were trying to do. So they take the original one and then tear them apart and then add at the end of it and then use this one entirely as an input to your neural network. So you can use some weights and then you can get a neural network and then you have another output that also does the same thing, and then you patch these pieces together. So if this size is larger than this size, this is what you are calling a convolution operation. So what we want to do in transpose convolution is the reverse of it, where you have this is smaller, the other one is bigger. So you want to go in this direction. So what we want to do is, ideally we want to get the right transformation operator, but that is computationally very expensive. So we are ensuring that at least the dimension is proper, and the relations that we have here are going to be same. So these are the constraints that you have, that these weights have to be equal. This is one constraint that you have. These zeros essentially denote the sparsity of your thing. These two features are something that we want to preserve, and yet get the same, like this will ensure that you have the same computational complexity, and you also need to ensure the dimension is same. So if you use C, you are getting one dimension. You just use C transpose, you will get a different dimension. That is the whole idea here. And if you want to do this transpose convolution using sliding window, to visualize that is something that cannot be done in this way, because it is defined in a slightly different way. To give you an intuition, one way of treating that is the one that we have discussed just now. So you can assume it to be like as if you are adding padding, but you are not doing it at the boundaries, you are doing in between. So you can assume it to be like this. So this is your 3 by 3. So this is not what is happening inside a transpose convolution, just to give you a visualization. So what we are trying to do is initially do the padding and convert it into 5 by 5. So I will add a 0 layer here, and again the normal layer. Again I will add a 0 layer here. Similarly, I will do the same thing along the other direction. So I will add a 0 layer here, the normal layer, a 0 layer, and the normal layer. So originally if it was a 3 by 3, I do this. So this becomes a 5 by 5, and then on this I will apply a kernel to finally give, say if I apply a 2 by 2 kernel, I would get a 4 by 4 one. So from 3 by 3, 5 minus 2 plus 1 is 4 by 4. So from 3 by 3, I was able to upscale to 4 by 4. This is exactly not what is happening, but this is something that can help you to visualize this. So what we are doing in transpose convolution is unlike convolution plus padding, where you are giving more representation to just the boundaries, because you are adding zeros only outside the boundary. What is actually, how you can visualize this is you are adding zeros in between the elements instead of adding them only at the boundaries. Now what happens is, now the boundaries are not like the previous case, you also add along the other directions. So even at the boundaries, so this becomes say 7 by 7. This is going to be 6 by 6. So just know, like you have added padding of 4 just outside. Now what we are doing, we are adding padding, but we are adding all 4 at different places. One is added here, second one is added here, third one is added here, and fourth one is added outside the boundary. So this way you will ensure that padding is there, but then you are not giving so much importance to zeros, and all of the elements also get some representation in it. Does this help you, or did it make you more confused? Do the weights of convolution need to be constrained to -1 to 1? There is no constraint as such, but the only problem that you will encounter is because of this finite precision thing. If your weights are exceeding those values, when you multiply with the image intensities and so on, it will keep on increasing. So if you have some number greater than 1, and if you multiply with some number greater than 1, it just keeps on exploding. That is something that you want to prevent. So we usually don't use values. Values will be actually between 0 to 1 instead of -1 to 1, or whatever, -1 to 1. So you want to restrict it to some fixed values, otherwise it will just explode. You can have the other scenario as well. If you use values less than 1, it could so happen like 0.1 times 0.1 is just going to be 0.01, and then you multiply, and then it keeps on decreasing, and then you have zeros. That is something happens with your gradients. That is called vanishing gradient. I think it will be discussed a little later once recurrent networks come. But the idea is that you want to restrict it to some fixed values to prevent that exploding one. Any other queries with this before going to the final question? The final question essentially asks you to calculate to do backpropagation for a convolution network. It's like you have already done backpropagation in the last assignment, but that was for a fully connected one. So how do you do it for a convolution network? Is it going to be any different, or how different? That's the things we will see that. Okay, if there are no questions, then maybe I'll go through a little math first, and then we'll actually substitute the values. Before you can substitute the values and do it for yourself. I'll just take it for a general case. So here we have an input x, which is 3 by 3, and then I'm applying a kernel. This is for convolution operation, 2 by 2, and I'm getting an output of say 2 by 2. So if I were to, I just don't take the values, so that if I take values, it might get confusing. So if this is my matrix, kernel, as before, we will use W1, like W for the elements in the kernel. I'm doing some operation on this, and I'm going to get and just as a caution, so I have this is just for an explanation purpose. Don't try to, like, if you want to write your own code, do not try to implement it in this particular way. This is not the most efficient way to implement it. If you want to implement it yourself, and anyway, I don't think you have to implement it yourself. This has already been implemented, and most optimized versions are already available. If you are using TensorFlow or Keras or PyTorch or whatever framework you are using, they are already available. You can use them directly. So don't try to implement it in this particular way, because as I've mentioned, like writing it in this matrix form is itself memory intensive. You are just storing zeros, which is just waste of memory. So don't try to implement it in this particular way. There are more efficient ways which you can look up. I don't want to discuss that in the course. You can look it up yourself, and then you can find those ones. Yeah. Coming back to this. So what is y11? So let's write for one equation, so others you will be familiar with. So how do I get y11? This particular element is obtained by taking this kernel on these 4 elements. So y11 is going to be w11 Similarly, you can have all other values, 2, 1 and 2, 2. Or if you are comfortable with the original notation that I have introduced before, you can write yij as essentially summation of m comma n. So this essentially is 2 summations you have to do along rows and columns. I am just writing m comma n, so this is equivalent to 2 summations of yi yi plus m j plus m times your input times your kernel. This is what we have discussed previously. Using this formula, you calculate yij for all locations. Once you get all locations, what you do, you have y actual of I comma j is something that you are already provided with. So if I define my loss function or objective function as y minus ya whole square, so this you have to do for all the elements and then apply a summation. So sigma over I comma j, I do it for this. So this is my objective function. This is how I define my objective function. So now what we do in backprop, what do I require? Ideally what we want is to identify the weights inside the kernel. So my objective is to identify W11, W12 and all of them. So we will use, say, steepest gradient descent. So in order to do steepest gradient descent, I need to know what is the value of grad Wj, or essentially I need to know the value of del z by del w. This is something that I wanted to know. So how do I calculate this from this? So we use a chain rule. So first you do with respect to y, and then you apply y with respect to w. So just to stick with the notation, so we will write this as, this can be written as, like you have several values of I and j. So let's say for particular value of I comma j times, see we are using the notation m and n for this. So if I want to do for m and n for a particular value of mn, it's going to be summation over I comma j. You just apply the chain rule, so 2 times y ij minus y actual ij times del y, I am just writing subscript here just to save some time, by del w mn. So yeah, one thing that I have not written, I don't know why I haven't asked the question. So this is just the normal convolution. There is no two things. I have left out 2 things. One is activation function. You need to apply a nonlinear activation after doing this convolution, and then there is a bias term. This is something that you need to add. I have assumed that this is a linear activation, so there is nothing, and then say bias is 0. So this equation is only for this particular scenario when you have linear activation and then there is no bias term. That is when you have your output is given by this. So in that particular scenario, this is what you will be getting. So this is my error term. So I can write this as some error of I comma j times del y ij by del wmn. So what is this value? Del y ij by del wmn. So this is my y ij. Yij is summation over mn x I plus m. That's k of mn is essentially your weight, so that is wmn. So using, so this is say 1, this is 2. So if I substitute 2 in 1, what will be the value of del z by del wm? Summation over I comma j. So only for this particular weight you will have, so when you differentiate with respect to mn, only for one particular value of mn that matches this, you will have this particular coefficient, and everywhere else is going to be 0. So this will give you error of I comma j times del yij by del wmn is going to give you this coefficient x of I plus m j plus n. So now if you compare this equation with this equation. You can see like the only difference here is here I was having some kernel k of m comma n. So instead of that I have I comma j. So here the summation was over mn, here the summation is over ij. So this is I plus m j plus n is the same as here. So this is exactly kind of similar to this one. So this entire equation is essentially a convolution operation. The only difference is you are convolving x is your input and you are convolving with your error. Okay, let me ask one more question before actually going any further. So say there are two things, A and B. So is this convolution operator commutative? It's like, are these equal? Can I do A, B and B, A and do we get the same answer? So essentially when I am doing this summation, can I replace I plus m, j plus n? Yeah. So to those of you who are from the background of say signal processing, if you have some background in signal processing, there you might have heard this term called convolution. Say, I don't know, for of you who are familiar with Fourier transform, so you apply the convolution operation in time domain is equal to multiplication in convolution and things like that. So there you usually have this commutative property to be true, but which is something that doesn't happen here. The only difference is the one we are calling convolution is really not a convolution that we are calling. So mathematically this is called cross correlation. The operation that we are doing now, this operation is called cross correlation. It's not convolution in the strict sense, but we are just using the name like that. Yeah, anyway, the point that I want to highlight here is it's not commutative. So now the properties that we have for convolution are: one, it is only invariant to translation, it is not invariant to rotation scaling, and now we know that it is not commutative also. Now coming back here, so what we have to do is you have to just use your error as your kernel and then do the convolution on your x. X is the previous input layer, then you should directly get this value, and this is the value that you will be using to update your particular weight. So if you use the steepest gradient descent, Wmn at I plus 1 step is going to be Wmn in minus some learning parameter times this. So I hope this is clear. Now with this background, can you solve for this particular example? So my loss function or my j is here given as y minus same function as before. So this is my input, this is my kernel, this is my actual. So can you calculate del j by del w? So I want for all the weights. So if I want to for all the weights, it's going to be a matrix, say of size 2 by 2, because I have 4 weights here. So can you calculate this quickly? It's just a bit of math, nothing more, so I just don't want to spend more time on it. So you can use this relation, from there you should be able to calculate. Just bring the matrices here, so it will be easy for you to see both. So these are my inputs, and yeah, so this is the relation. I am asking you to find the value of this. So what would be your first step is to calculate error. So x is your input, you have to do the convolution operation. Stride is 1, padding is 0, you get y. From this y you also have the information of y actual, from that you calculate L. Now you do the back propagation. So from this from here you will have the error term, use that error as kernel with same stride s equal to 1 and padding equal to 0. From there you will calculate your gradients. So here it is error, but ideally what will happen in any, like here there is just one layer, so you don't have much problem, but you have more layers, this error is going to be the term that you have from the previous layer. So this is say if you have layer 1 to layer 2, whatever gradients you get here, loss or gradient of the loss. This will be your kernel, and this you will apply on the previous input layer. So this will be my x. If it is between two layers, here it is just the final layer, so you just have the final error term. Ideally it would be the gradient term from the previous layer. Okay, maybe you can do this for this one problem, and then this is the last problem, so we can conclude the session once you are done with it.
Error is equal to 0 minus 570.
So what was your y value? Okay, you are directly giving me the error value. So what was your error? 0
minus 5. Second row is 700.
which means your y was
Second row first element is plus 7.
plus 7. Okay, so your y would have been something like what, 36, 31, 43 and 49. This was your y. So if you apply this convolution on this is what you get as y, and then you subtracted this from this, and then you got an error term like this. Now if you apply this convolution, so how did you get your error term? You just subtracted these two. There is a 2 times, so okay, did you multiply with 2 already, or you just subtracted this? So 2 plus 8 plus 10, 25. I think you might have to multiply with the 2 right here. So like my objective function has y minus the square, right? So because of this square, when I do the differentiation, my error term is going to have 2 times the difference of this. So this is after you apply a 2. I think you forgot to apply a 2 here. So let's do this convolution once. If you apply this on here, what is the value you get? 3 plus 10 plus 18. 3 plus 10 plus 18. 13, 18 is 31, right? So how is this 30? 31. So this is 25, 31. So the difference is 5. So this is going to be minus 10, right? So whatever you got, you multiply with a 2.
Minus 10 plus 14.
Yes. So this is 14 and 0. Now if you apply this convolution on x, what is the value you are getting? So like use this as your kernel. So instead of the original weights, now you use this error term. Should we do ya minus y or y minus ya? So what is the expression I got here? So I got y minus ya, right? It's like, how should it matter? As long as like it tells you that you, okay, so this is my objective function. When I do my derivative, this is what I would be getting, right? If you are using the other way around, then you would have a minus sign here, and when you do this derivative, you will have another minus, and both of them can cancel out, right? It's like, what I mean to say is, if you declare it in a reverse way, so your j is essentially ya minus y whole square. So when you do the derivative of this, you are going to get 2 times ya minus y times you are going to get another minus 1 because you have to do this one. So minus 1 times del y by del w. So this will essentially again become 2 times y minus ya. So all you have to do is y minus ya. Okay, here it is the other way. No, I think it's y minus ya, right? 36, 31 minus, that's why there is a minus 5. I think there is some confusion. So I declare it, the objective function is defined as y minus ya is the actual one. So it is y minus ya, so your error term is y minus ya, it's not ya minus y. Okay, yeah. So did you get the final values of del z del w? So you have to just apply this convolution on that. So basically take this thing, overlap here, minus 20 plus 16 something, and then you have apply this on the second one, so minus 30 plus 14 5 70. Okay, these values are too high. Minus 20 plus 56, so much, 36, right?
First element minus 20, 16 plus 64.
64. Why is that? 14 4 56, right? Now I'm just checking whether these elements are correct or wrong. So if these are wrong, this will go wrong. So if this is so if you apply this on this kernel, so you have 4 times 0 plus 5 plus 14 19 plus 24 is 43. So this is correct. 25 is correct. 31 is correct. So if you check the last one, so 6 plus 16 22 plus 27 is 49. So this is correct. If you do the subtraction, so you have minus 5, and then 43 minus 36 is 4 plus 3 7, and then you have a 0. So this is correct. You have to multiply with 2. So you got these error terms correct. Now if you apply this here, what is the third term? So now I want to apply this with this. So 4 minus 50 plus 73 minus 50 plus 14 7s 98, and then you have minus 60 plus 112. So whatever values you get, these will be your gradients, and this is what you will be using in this particular step to update your weights. 36 40 48 52. Okay, 36 40 48 52. Okay, you got some answer. So these are the updates for each of the weights. You can update it directly from here. Okay, so I think this is the last question I have for this week. So I think this is clear. So you understood how to do the backprop. So if you want to implement it algorithm, like if you want to implement it yourself, all you have to do is use the same backprop algorithm that you have before, but there you would be just doing multiplication, like you would be applying the layers in a reverse way. Here you would apply the convolution layer. That's the only difference. Now let me ask you one question. So say instead of convolution, if my original operation is transpose convolution, sir, when we do gradient scaling, will be divided by 14 years now. Okay. In what context you are asking? So were you asking with respect to the optimization algorithm or somewhere else of this gradient matrix? So I haven't done any scaling here. Okay, in the optimization algorithm. Okay, here if you want to do, we have discussed this, like you have different types of algorithms, so each one does this differently. Usually the scaling will be done in terms of the previous gradients you get, like we discussed in EDA grad and EDA delta, right? So we take the previous gradient and then from there we do the scaling. But if you want to do just to ensure that this matrix is well conditioned, you can do with maximum scaling or Frobenius norm. I haven't done like that, but as long as just that you want these values to be between 0 and 1, that's why you are doing that. It should make sense. But why do you want to do gradient scaling anyway? Just to prevent the exploding or something? Okay. Just to prevent exploding, you don't have to do the scaling because the optimization algorithm already takes care of that. Like essentially here itself you do the scaling with other gradients, so it just won't blow up. If the value here itself is blown up, that is when you would be doing the scaling. Okay, if that is the case, then we don't have anything with optimization to do. Yeah. I think all the variants for the assignments are covered. So are there any other questions in the assignments? I think we have covered most of it. Backprop is not there in the assignment, but it was there in the session. Then we have this is something that is covered. How to do transpose convolutions covered. I think this matrix sizes are clear. So yeah, so pretty much covered everything. So are there any other questions? If not, then yeah, if you have any questions, you can stay. Otherwise, you are free to like you can drop out of the session. Yeah. Thank you for joining. Thank you. Yeah, as there are no further questions, we'll conclude the session for today. Thank you for joining. We will meet the next week.